The observable universe is the part of reality that human beings can detect and study with the tools of science. It is not the entirety of existence, but only the section we can glimpse through the light and radiation that have traveled far enough to reach us across billions of years. From the surface of Earth, and from telescopes orbiting high above its atmosphere, we have gathered fragments of information, photons that left their sources long ago. Piece by piece, these fragments allow us to form a mosaic of the grand stage on which all cosmic events play out. Yet, as magnificent as this cosmic window is, it has limits. There are strict horizons that even our most advanced instruments cannot cross. These barriers are not simply technological, they are fundamental, written into the laws of nature. At the heart of these limits lies light itself. Light is more than a source of illumination. It is the messenger of the universe, the carrier of ancient news. Each photon is a time capsule, whispering to us from across gulfs of space and time. When a photon finally strikes a telescope's mirror or a satellite's detector, it tells a story that began long before humanity even existed. But light travels at a fixed pace, about 300,000 kilometers per second. On human scales, this is unimaginably fast. A beam of light could circle Earth more than 7 times in a single second. Yet on cosmic scales, this speed sets a firm boundary. We cannot see farther than light has had time to travel since the dawn of the universe itself. That is why astronomers say the observable universe is about 93 billion light-years across, even though the universe is only 13.8 billion years old. At first glance, this seems impossible. How could something younger than 14 billion years stretch nearly 100 billion light-years? The answer lies in the expansion of space itself. Since the Big Bang, space has not been static. It has been stretching, carrying galaxies along with it like dots on the surface of an inflating balloon. As light makes its journey across this expanding stage, the space it travels through is also growing, which makes the distance between us and the source far larger than the time it took the light to begin its voyage. This is why we see galaxies not only as they are, but as they once were, ancient snapshots frozen in time. When we gaze at a galaxy 10 billion light-years away, we are looking back 10 billion years into history, observing it as it was when life on Earth had barely begun. Every image we capture is both a portrait of space and a window into the past. And yet, even this colossal view is only a sliver of the true cosmos. Many scientists believe that what we can see is a fraction of a much grander reality. According to theories of cosmic inflation, the universe beyond our horizon could be at least 10 to 23 times larger than the observable region. That is a number so enormous it defies human comprehension. It suggests that the observable universe, already staggering in its size, is only a tiny slice of an almost infinite whole. To probe this slice, humanity has built instruments of astonishing capability. The Hubble Space Telescope, launched in 1990, gave us breathtaking deep-field images that revealed thousands of galaxies packed into a single patch of sky. What once appeared empty turned out to be overflowing with cosmic structures. Today, the James Webb Space Telescope has taken this mission further. Its infrared vision peers through cosmic dust, revealing galaxies that formed just a few 100 million years after the Big Bang. Webb has also given us the ability to analyze the atmospheres of distant exoplanets, detecting chemical signatures that hint at conditions far from Earth. These breakthroughs expand not just our scientific knowledge, but also our sense of possibility. Yet profound mysteries remain. What lies beyond the horizon of what we can see? Could there be regions of the universe with completely different laws of physics? Could there be other universes entirely, parallel realms beyond our reach? Ideas such as wormholes and warp drives continue to ignite the imagination. They represent humanity's attempt to think beyond the rigid boundaries of physics as we currently understand it. A wormhole, in theory, could act like a hidden passageway, connecting two distant points in the universe through a tunnel in spacetime. If such a bridge could exist, a journey that might otherwise take billions of years could, in principle, be made in moments. A warp drive, by contrast, would not move a spacecraft faster than light directly. Instead, it would bend space itself, compressing it in front of a vessel and expanding it behind. Within this bubble, the ship would ride along, bypassing the cosmic speed limit without technically breaking it. These ideas remain speculative, and for now, no evidence shows that they are achievable. Many physicists argue that they may require exotic forms of matter or energy that could be impossible to create. Yet, even as hypotheses, they remind us of humanity's refusal to stop exploring possibilities. They demonstrate that curiosity will always push us to imagine what lies beyond the edge of the possible. But the questions we ask are not limited to physics or the structure of space. They also reach into something even more profound: life itself. The question, "Are we alone?" may be the most important one humanity has ever asked. So far, astronomers have confirmed the existence of more than 5,000 exoplanets. These are worlds orbiting stars far beyond our solar system. Some are gas giants, some are rocky planets, and a growing number lie in the so-called habitable zone, where temperatures might allow liquid water to exist. Water, as far as we know, is a key ingredient for life. Its presence changes the search from a theoretical exercise into a tangible possibility. One of the most striking milestones came from the James Webb Space Telescope's study of WASP 96b, a massive planet larger than Jupiter. Webb detected water vapor, haze, and clouds in its atmosphere. This did not prove the existence of life, but it proved something equally important, that our instruments now have the power to probe alien skies. We can begin to look not just for planets but for conditions, chemicals, and atmospheres that may one day point us toward living worlds. Each discovery draws us closer to the dream of finding another Earth, or at least another world capable of sustaining life. Some scientists look inward, to our own solar system, for nearby possibilities. Beneath the icy crusts of moons like Europa and Enceladus, vast subsurface oceans may exist, warmed by tidal forces and chemical activity. Such environments could, in theory, harbor microbial life even without sunlight. Others cast their eyes outward, to the thousands of exoplanets scattered across the Milky Way, imagining civilizations that may have risen and fallen long before humanity took its first steps. For now, the evidence is silent. No unambiguous sign of life has been detected. Yet the growing body of discoveries makes the search more urgent, more compelling, and more hopeful. It feels as though humanity is on the threshold of an answer that has eluded us for millennia. And still, even beyond this search, the cosmos presents deeper mysteries. Dark matter is one of them. Invisible, undetectable by ordinary light, it outweighs visible matter by a factor of 5. We know it is there only through its gravitational influence, bending light, shaping galaxies, and weaving the large-scale structure of the universe. What it is made of remains one of the greatest scientific puzzles. Then there is dark energy, a force even more mysterious. It appears to be driving the acceleration of the universe's expansion, pushing galaxies away from each other faster and faster over time. Together, dark matter and dark energy account for about 95% of the cosmos, leaving only 5% for the matter that forms stars, planets, and people. In other words, everything we know, the atoms of our bodies, the light of the stars, the worlds we study, is only a tiny fraction of reality.